In this presentation, we will learn how to add two polynomials with the help of linked list. So without any further delay, let's get started. Let's say we have these two polynomials 3x squared plus 2x plus 1 and 5x squared minus x plus 2. These are the two polynomials we are available with, and our target is to obviously add these two polynomials. Okay. Addition of two polynomials involves combining like terms present in the two polynomials. Now, what do we mean by combining like terms present in the two polynomials? What do we mean by like terms? This simply means adding terms having same variables and same exponents. Like terms are those terms which have same variables and same exponents. Okay. We have to add these terms only. This is what addition of two polynomials means. We simply want to add these two polynomials. Now, what do we mean by this? We must add their like terms, right? Here you can see that 3x squared and 5x squared are like terms because the variables of these two terms are same and the exponents are also same. So here we just have to add these two terms, right? Now here we can see that this is 2x and this is x. Obviously the variables are same and the exponents are also same. Here obviously the exponent of x is 1 and the exponent of this x is also 1. Here we have x to the power 0 and here also we have x to the power 0. Therefore, these two terms are also like terms. It is clear that in these two polynomials, 3x squared and 5x squared are like terms. Similarly, 2x and x are also like terms, and 1 and 2 are also like terms. Now let's just add these two polynomials. The resultant polynomial must look like this: 8x squared plus x plus 3. Addition of two terms simply means adding their coefficient. Here you can see that these two are like terms, so we must add their coefficients. You can see that 5 plus 3 gives 8. That is why we got this term as a result, that is 8x squared. After this we have 2x and minus x, and obviously we know the result will be plus x. And here we have 1 and 2. Obviously addition of these two numbers gives 3. Now we know addition of two polynomials becomes easier if the terms are arranged in descending order of their exponents. You can clearly see this also, that the addition becomes easier when the terms are arranged in descending order of their exponents. Order is important. Now let's see the procedure for adding two polynomials. Let's say we have the following two polynomials and our job is to simply add them. Let's say we are available with these two polynomials and our job is to add them. Terms are arranged in descending order of their exponents. You can clearly see this, that in these two polynomials, terms are arranged in descending order of their exponents. This makes the addition operation easier. We'll see that why in a moment. Let's represent the above two polynomials using linked lists. Obviously, in programming, we must represent these two polynomials with the help of linked lists. And here is the linked list representation of the first polynomial, that is this polynomial. Here you can see we have 3 nodes in total because in this polynomial we have 3 terms: 5x to the power 6, 6x to the power 4, 2x to the power 3. In the previous lecture, you have already learned how to create a linked list equivalent to the polynomial, and that too in descending order of their exponents, right? Maintaining the order as well. Here you can see 6 comes first, then 4, then 3. This part represents the coefficient part of the term, this part represents the exponent part of the term, and this represents the link part, which means this consists of the address of the next node of the list. This shaded region simply means that there is no node after this node. Okay. Now here comes the linked list representation of the second polynomial. This is how the linked list of the second polynomial looks like. Here obviously we have 4 different nodes because here we have 4 different terms, right? And here you can see this, that head 1 pointer is pointing to the first node of this list and head 2 pointer is pointing to the first node of this particular list. Now adding two polynomials means adding their like terms. This is the simple thing we must always remember, right? Adding two polynomials means adding their like terms. And this simply means that adding their coefficients. The only thing we have to do is to compare their exponents. Obviously, we must compare the exponents of the terms. Whenever the exponents are same, we can add them. Now here you can see we have this polynomial 1 and polynomial 2, right? Our target is to simply add them. Let's compare these two terms. And comparing these two terms means comparing their exponents. Here you can see the exponent of this term is 6 and the exponent of this term is also 6. 6 is equal to 6. Therefore, these two terms are like terms. We can conclude this because their exponents are same. And obviously variables are same as well. Therefore, these two terms are like terms. And hence we can add their coefficients, and this is what we will get as a result. That is 13x to the power 6, right? Because 8 plus 5 is 30. After this, we must compare these two terms, that is 6x to the power 4 and 3x to the power 2. And comparing these two terms means comparing their exponents. You can clearly see this that 4 is greater than 2, isn't that so? This simply means that this term is greater than this term, and these two terms are not like terms, right? Hence we cannot add them. Now what we will do? We will simply select the term which has the highest exponent. You can clearly see this that this term is having the highest exponent. Therefore, we will select this term and we will add this term in the resultant polynomial. That is what we will do. And after this, the next step is to simply compare these two terms. Obviously, because we have selected this term and now we must compare these two terms, right? Now you might be asking this question why I am simply adding the term which has the highest exponent, because I have to maintain the descending order in the resultant polynomial as well, right? This is important. I have to maintain the descending order of the exponents in the resultant polynomial. That is why I'm always preferring to add the term which has the highest exponent, right? Now let's compare these two terms, that is 2x cube and 3x square. You can clearly see this that 3 is greater than 2. Hence, we can add this term in the resultant polynomial. Now you can see that terms of polynomial 1 are finished. And this means that we will put all the remaining terms of polynomial 2 in the resultant polynomial, because 3x square cannot be compared with any other term in the polynomial 1. All the terms of polynomial 1 are now finished. That's why we will simply add all the remaining terms of polynomial 2 in the resultant polynomial. These are all the remaining terms, right? So we'll simply add them in the resultant polynomial. So the resultant polynomial must look like this. That is 13x to the power 6 plus 6x to the power 4 plus 2x to the power 3 plus 3x to the power 2 plus 4x plus 5. You can clearly see this that the order is maintained. Here you can see that the exponents are properly arranged in descending order. This means that terms are arranged in descending order, and that too depending on their exponents. In a linked list representation as shown below, the addition operation is easier to perform because the two polynomials represented by the linked lists are arranged in descending order. As I've already told you, the addition operation becomes easier when the two polynomials are arranged in descending order. And obviously this means that the linked lists which are representing the polynomials must be arranged in descending order of their exponents. Here obviously you can see this in this linked list. The first node has this exponent, that is 6. Next node has this exponent 4, and the last node has exponent 3. Here in this polynomial, the first node has exponent 6, second node has exponent 2, third node has exponent 1, and last node has exponent 0. These two linked lists are properly sorted according to the exponent part of their nodes, right? This is always advisable because this makes the addition operation easier, right? Now imagine, if the terms are not arranged in descending order of their exponents, then what will happen? In that case, obviously, the addition becomes difficult. You can clearly see this, that the exponent part of this node is same as the exponent part of this node. They are in the same position, hence it is easier to add them. But what if this node is not the first node but the last node of this linked list? Obviously, the addition becomes difficult, because in that case, I have to traverse this whole list in order to find the term which is equivalent to this term. And this means that I have to search this entire list in order to find the exponent which is same as this exponent, right? Now this is obviously difficult. This increases the time complexity, okay? This must always be avoided. That is why we are maintaining this order, right? Now, let's see the algorithm behind addition of two polynomials. Repeat the following until PTR1 or PTR2 becomes null. Here you can see PTR1 pointer is pointing to the first node of this list, and PTR2 pointer is pointing to the first node of this list, right? We will repeat the following algorithm until PTR1 or PTR2 becomes null. Obviously, we will use these two pointers for traversing the lists. Now, if PTR1 expo is equal to PTR2 expo, if the exponent part of the two nodes are same, then add the coefficients and insert the newly created node in the resultant linked list and make PTR1 and PTR2 point to the next nodes. This is simple, right? If the exponents are same, we will simply add the coefficients and we will put the result of this addition in the newly created node, and obviously we will simply add the exponent to the newly created node, and then we will move these pointers towards right so that they can point to the second node of the lists, right? If PTR1 expo is greater than PTR2 expo, if it is the case that PTR1 expo is greater than PTR2 expo, then insert the node pointed by ptr1, because the node which has the highest exponent must be added to the resultant linked list, right? And then after that we will make ptr1 point to the next node. This makes sense? Now if ptr1 expo is less than ptr2 expo, in that case insert the node pointed by ptr2 in the resultant linked list and make ptr2 point to the next node. This is the complete algorithm. It is simple to understand. Now here is iteration 1, okay? Currently ptr1 pointer is pointing to the first node of this list and ptr2 pointer is pointing to the first node of this list. Here is the resultant linked list looks like. Currently head 3 pointer is pointing to the first node, and here we have just one node in this resultant linked list, because we can clearly see this that the exponent part of these two nodes are same. Hence we can simply add the coefficients and put the result in this resultant node. Here you can clearly see this that 8 plus 5 is 13. So we'll put 13 over here and we'll put 6 as it is over here. That's it. And obviously this must contain null, right? Now after this, we will move both the pointers towards right, and then we will compare the exponent part of these two nodes. Here you can see 4 is greater than 2. Hence we will put this node in the resultant linked list, right? And we will simply move this pointer towards right. Now we will compare these two nodes. Comparing these two nodes means comparing their exponent parts. Here you can clearly see this that 3 is greater than 2, right? Hence we will simply put this node in the resultant linked list. After this iteration, ptr1 becomes null. Isn't that so? After iteration 3, ptr1 becomes null. Now there is nothing to compare with ptr2 expo. At this stage, we must add all the remaining nodes of the second linked list at the end of the resultant linked list. For this purpose, we must have to add this particular code. Repeat until ptr2 not equal to null. Insert the remaining nodes. Also, in general sense, we must also add this piece of code as well, because it might also be possible that polynomial 2 gets finished before polynomial 1. In that case, this code will work. Repeat until ptr1 not equal to null. Insert the remaining nodes. Okay. Now here you can see that we are done with the first polynomial. Hence we will add all the remaining nodes of the second polynomial. ptr1 is null, right? We will repeat until ptr2 becomes null, and we will add all the remaining nodes in the resultant linked list. First we will add this node in the resultant linked list, then we will add this node, and then we'll move pointer towards right, and we will add this node, and this is the resultant linked list so obtained, right? And after this, obviously ptr2 becomes null, and this means this is the resultant linked list so obtained, right? This represents the resultant polynomial, the addition of these two polynomials, right? Now let's see the complete code in code blocks. Here you can see this is the complete code. Here we have struct node, which consists of float coefficient, integer expo, and struct node star link, right? Then we have this insert function, which I have taken from the previous lecture. We have this create function. I took this from the previous lecture. And this print function also I took from the previous lecture. And here we have polyadd function. Let's see the main function first. Here you can see that I have declared a head1 pointer and head2 pointer, because I want the user to enter the first polynomial and enter the second polynomial. Here you can see that I'm calling the create function twice. This particular function helps us in creating the linked list, which is equivalent to the polynomial. And here you can see this is how create function looks like. And here I'm calling the insert function also, which looks like this, right? If you have any doubts that how this code works, then I would recommend to watch the previous lecture first, okay? Here after this, I'm simply calling the polyadd function and I'm passing head1 and head2 to it. It will add the two polynomials. And this is how this polyadd function looks like. Here I have declared 2 pointers, right? And here we have head3 pointer, which is currently holding null. This pointer must point to the first node of the resultant linked list after completion of this code. And this is the logic, that is, we have a while loop where I have put this condition ptr1 should not be equal to null and ptr2 must not be equal to null. Then we can continue. Here you can see that if ptr1 expo is equal to ptr2 expo, then I'm simply calling the insert function to create the new node and insert the new node in the resultant linked list. Here for this purpose, I have passed the head3, then ptr1 coefficient plus ptr2 coefficient. Obviously, we must add the coefficients, right? And also you can see that I'm passing the exponent of the ptr1. You can also part the exponent of ptr2. At the end, they are same, right? So this insert function will create the new node and will add that node in the resultant linked list, right? And obviously, then we must increment PTR1 and PTR2. And after this, you can see we have this else if, and we are checking this condition. If PTR1 expo is greater than PTR2 expo, then we will call the insert function. And here you can see I'm passing PTR1 coefficient and PTR1 exponent, because PTR1 expo is greater than PTR2 expo. And here in this case, I'm passing PTR2 coefficient and PTR2 expo because PTR1 expo is less than PTR2 expo, or PTR2 expo is greater than PTR1 expo. So this is the complete logic. After this, we have this while loop, PTR1 not equal to null. And here also we have a while loop where I'm checking this condition that PTR2 must not be equal to null. And here I'm simply calling this insert function and passing PTR1 coefficient and PTR1 exponent. And here I'm passing PTR2 coefficient and PTR2 exponent. Finally, I'm printing this message that is added polynomial is, and then I'm calling this print function. Okay, and this is how this print function looks like. This is the print function. This function we have already seen in the previous lecture, right? Only this piece of code is new in this whole program. Rest of the code is same as what we have seen in the previous lecture. Let me just execute this code. It is asking us to enter the first polynomial, and it is also asking us to enter the number of terms. Let's say I want to add 3 terms. Enter the coefficient for term 1. Let's say this 23, and the exponent is 6. Enter the coefficient for term 2. Let's say it is 2, and it is 4. Enter the coefficient for term 3, let's say it is 12, and the exponent is, let's say 3. Now we will enter the second polynomial, and for this purpose we must enter the number of terms of the second polynomial. Let's say it is 4. Enter the coefficient for term 1, let's say it is 12, and the exponent is 6. Coefficient for term 2, let's say it is 7, and the exponent is 3. And for the third term, let's say the coefficient is 25. And the exponent is, let's say, 5. And let's say the coefficient for term 4 is 43 and the exponent is 1. So here is how the added polynomial looks like. Here we have 35x to the power 6, 25x to the power 5, 2.0x to the power 4, 19x to the power 3, and 43x to the power 1. There are total 5 terms in this polynomial. Okay? Okay friends, this is it for now. Thank you for watching this presentation.